Welcome to the deep dive. Today we're getting into something that, well, if you use a smartwatch or any kind of wearable, you've definitely run into missing data. You forget to charge it, maybe it slides off a bit, the signal drops, and suddenly your health data has these annoying holes in it. But here's the real kicker. What if that data, the stuff meant to tell us about our health, is always incomplete? Like fundamentally. It's not just frustrating for us. It turns out this is a huge headache for the big AI models, foundation models, that are supposed to learn from all this data. They kind of expect perfection. And, real life isn't perfect. So my first thought looking at this was, why is this such a deep problem for the AI? More than just, a gap for us.
That's exactly the right question. And it leads us straight to the paper we're digging into today. It's called LSM2, Learning from Incomplete Wearable Sensor Data. It's pretty new, from Google Research, DeepMind, and others, just published June 2025. And our mission really is to see how they're tackling this missing data problem head on. Not by trying to guess what's missing, but by actually teaching the AI to learn from the incompleteness itself.
Okay, that sounds different. So it's not about fixing the data, but making the AI smarter about the messy data we actually have. That could make our wearables way more reliable, right? Even if we don't have that perfect unbroken stream of data points. All right, so let's unpack that. Why is missing data such a big deal for these sensors and the AI? I mean, okay, a few missing minutes, does it really matter that much?
Well, it matters a lot, mainly because it's not just a few minutes here and there. Missing data in the real world is, it's everywhere. It's the norm. Think about why. Devices turn off sensors to save power, right? There's environmental noise, maybe the sensor's blocked, hardware glitches, or, people don't always attach them perfectly. Data transmission fails sometimes. And, of course, charging time. Every time it's off your wrist, that's a gap.
Okay, yeah, when you list it all out, it sounds like the data is mostly gaps sometimes.
It can feel that way. And this really hits those foundation models hard. The standard approach, self-supervised learning, or SSL, these models really complete neat data. They get confused or learn the wrong things when data is patchy. And here's the other thing. A lot of the really important health insights, think circadian rhythms, heart rate patterns, daily activity, you need a full day's worth of data, or close to it.
Right, you can't tell much about sleep from just 10 minutes.
Exactly. But day-long data always has missing parts. Always. And get this, the paper looked at 1.6 million daily records and the percentage of complete records.
Let me guess.
Low.
0%.
Wow. Okay. Not a single complete day in over 1.5 million example.
Not one. Every single day had some missingness. That really tells you the scale of the challenge.
So how did people try to deal with this before, if perfect data doesn't exist?
Well, the main ways weren't great. Option one, just throw out any data chunk that wasn't complete.
But that means you're only looking at tiny windows.
Right.
Like you said, useless for day-long stuff.
Precisely. Maybe less than 60 seconds sometimes. You lose all the context. Option two was imputation, basically trying to fill in the blanks.
Ah, like educated guessing?
Sort of. But the risk there is huge. You might fill it in wrong, introduce biases, and those biases can then spread through the whole AI model, making its predictions unreliable or just plain wrong.
Yeah.
It's like trying to patch a tire with chewing gum. It might look fixed, but it's not sound.
Okay, so filtering loses context. Imputation adds potentially bad data. Seems like a dead end. So if those old ways don't work, what's the actual breakthrough in this LSM2 paper? What do they do differently? They introduced LSM2, which is their second-gen large sensor model. But the key is this new technique, adaptive and inherited masking, AM for short. And the really novel part, it's a self-supervised learning method designed to learn good, robust representations directly from that incomplete, messy data. No imputation needed.
Directly from the incomplete data. Okay.
As far as they know, it's really the first time this has been done effectively for wearable sensor data at this scale.
Yeah.
It builds on an existing AI technique called masked autoencoders, or MAE. You might have heard of it. It's been big in vision and language.
Yeah, MAE, masking parts of an image or text and making the AI fill it back in.
Exactly. But AIM adds this really clever twist, specifically for the kind of missingness we see in wearables.
All right, let's get into that twist. How does adaptive and inherited masking actually work? How does it let the AI learn from data with holes without just, guessing badly?
Okay, think of your data like a puzzle again. Some pieces are already missing when you get the box, right? That's the real-world missingness. AIM calls these inherited masks. The model sees them, acknowledges they're gone.
Okay, so it knows about the real gaps.
Yes, but then, during training, the model also takes out more pieces itself, randomly. These are the artificial masks, and they're put only on the parts of the data that were actually observed.
Right, so it's creating its own practice problems on the data it does have.
Exactly. And here's the clever bit. The model learns to deal with both types of missingness. For the inherited masks, the real gaps, it learns to essentially work around them, to account for them without needing to fill them in. It accepts the incompleteness. For the artificial masks, the ones it created, its job is to reconstruct that hidden data. That's its training goal.
Ah, so it's learning about the data by filling in the artificial gaps, but it's also learning to cope with the real gaps by just acknowledging them.
Precisely. It uses a combined unified mask that includes both the real missing pieces and the artificially hidden ones.
Okay, that makes sense. But you called it adaptive and inherited masking. What's the adaptive part? Because the real-world gaps aren't neat and tidy, right? They vary hugely.
Exactly. And this is where it gets really, really clever. Standard MAE often masks a fixed percentage of the data, mostly for computational efficiency.
Right, easier to process if you know how much is missing each time.
But real wearable data isn't like that. One day you charge for an hour, the next day for 3. The missingness varies. So AIM uses 2 tricks together to handle this adaptively. First, it uses something called dropout removal. This lets it efficiently remove a fixed chunk of the data tokens, similar to standard MAE, which keeps the computation fast, like 25 times faster if you mask 80% of the data this way.
Okay, so that's the efficiency part, but what about the variable real-world gaps?
That's where the second trick comes in, attention masking. This is a mechanism within the AI model, the transformer architecture, that allows it to flexibly ignore any additional missing tokens, specifically those leftover inherited ones that weren't part of the fixed dropout.
I see, so it efficiently practices on a big chunk using dropout, but also has this flexible attention mechanism to just ignore whatever other real-world gaps happen to be there.
You got it.
Yeah.
Gets the speed benefits for training on huge data sets, but it doesn't break when faced with the unpredictable missingness of reality. It's efficient and flexible.
That balance sounds key.
It is. And they even tuned the types of artificial masking during pre-training to mimic real life. They used 80% random masking to simulate noise, 50% block masking of time slices to simulate the device being off for charging.
Like my overnight charge gap.
Exactly like that. And also 50% signal slice masking, which is like when one specific sensor, say the heart rate sensor, is turned off to save battery, but others are still on.
So it's training the AI on problems that look just like the ones it'll face with my actual data.
That's the idea.
Yeah.
And the crucial final piece is that this whole adaptive masking strategy isn't just used during training. It's used during inference, too, when the model is actually analyzing new data.
Ah, so it doesn't need some separate step to clean up my data before feeding it to the AI.
Nope. It operates directly on the raw, incomplete data stream. No external imputation, no throwing data away. The model inherently understands and handles the missingness. It's like it's fluent in Japanese.
Fluent in Japanese, I like that. Okay, so this AIM approach sounds really smart, but does it actually work? What were the results? You mentioned 40 million hours of data.
Yeah, a massive data set, and the results are pretty impressive across the board. LSM2 with AIM basically set new state-of-the-art performance levels. For generative tasks, basically, how well it can reconstruct missing data, it blew past the older methods. Like plus 33% better on one benchmark, plus 77% on another related to missing sensors, plus 47% on filling in a 10-minute gap. It's just much, much better at creating a complete picture from incomplete parts.
Okay, so it's good at filling gaps if you need it to. What about using the data for predictions, health predictions?
So that's where it gets really interesting. For classification tasks predicting things, they use just a simple linear probe.
Which, as we said, means testing the core understanding of the model, right? Not just adding lots of bells and whistles on top.
Exactly. And even with that simple probe, LSM2 beat previous self-supervised models, and even beat some fully supervised models, on tough tasks. Things like predicting hypertension, predicting anxiety, and recognizing 20 different types of activities.
Wow, beating supervised models is a big deal. That suggests it's learning really fundamental patterns.
It really does. The paper suggests it's picking up on subtle physiological cues that generalize really well. It also did better on regression, like predicting BMI, showing a plus 1.0% improvement in correlation.
So better reconstruction, better prediction, seems like a win-win. What about scaling? Does it get better with more data?
Yes, significantly better. It scales more effectively than the previous version, LSM1. More subjects, more data, more computing power, bigger models, all led to better performance. It suggests there's still headroom to improve further. It hasn't plateaued.
That's always good to hear in AI. But let's talk robustness. Real world means things break or sensors get blocked. How does it handle, say, losing an entire sensor feed?
Crucial question. And again, AM shows remarkable resilience. Take accelerometry of the motion sensor, super important for activity tracking. If you completely remove that sensor's data, LSM2's performance does drop by about 57%. But even with that drop, it still performs 47% better in absolute terms than the previous model, LSM1, did with the sensor.
Get out! So even crippled, it's
Right.
still better than the old state of the art.
Pretty much, yeah. Another example, hypertension prediction. Removing the PPG sensor, the one that measures blood volume changes for heart rate, causes only a 6% performance drop for AIM compared to an 11% drop for LSM1. It's just much less phased by missing inputs.
That really speaks to real-world usability. Your insights don't just collapse if one part of the data stream goes down.
Exactly. It means more reliable health monitoring, even with imperfect device usage or function. But maybe the coolest result, the real aha moment, is how it degrades. Its performance changes actually reflect known medical science.
What do you mean?
Okay, take hypertension and anxiety prediction. The model performs better using nighttime data. If you remove the nighttime signals, prediction accuracy drops by about 5% for both. But if you remove daytime signals, the drop is tiny, like 0.4% for hypertension, 0.01% for anxiety.
And why is that significant?
Because clinical research shows that nighttime biosignals are often more diagnostically valuable, they're less noisy, less affected by your daily activities. The AI figured this out implicitly. Its nocturnal advantage mirrors clinical knowledge.
Whoa. Okay, that's not just robust, that's intelligently robust. It learned why certain data is important.
Exactly. One more quick example. Anxiety prediction drops 11% if you remove the accelerometer, but barely drops, like 0.5% if you remove other sensors. And again, research has shown that motion data from accelerometers is really important for distinguishing anxiety-related physiological changes from just, changes due to physical exertion.
So the way the model's performance dips, it actually tells you something about the clinical relevance of each sensor for that specific task.
Precisely. It shows it's not just pattern matching. It's learning meaningful physiological relationships, respecting known temporal patterns and cross-sensor connections. The degradation itself is informative.
That is genuinely impressive. It feels like a big step towards AI that understands health data more deeply. Now, it sounds amazing, but research always has next steps, right? What are the limitations here or areas they're looking at next?
Sure. Well, as powerful as this is, the current study used specific, large, but private data sets. A big next step is applying and validating AIM on public data sets, something like the All of Us Research Program dataset in the US. That would really test its generalizability across diverse populations and data types.
Yeah, making sure it works for everyone.
Right. And also, the current model works with features summarized every minute, which is practical for handling massive day-long data. But working directly with the raw, high-frequency sensor signals is another level of challenge. More detail, but also way more noise and complexity, especially with gaps.
So processing the raw signal might be the next frontier.
Could be. Future work might look at better ways to combine features, maybe sensor-specific processing modules, before feeding into the main AIM framework, especially for those raw signals. But overall, this work really feels like a major leap. It's making AI robust to the messy data we actually get from wearables.
Yeah, it really seems like it. It means we can expect more reliable, more accurate insights from the devices we're already using. Imagine, your watch not just counting steps, but giving you a genuinely useful heads up about subtle health changes based on patterns over days. Even if you missed charging it last Tuesday or the signal dropped during your run, that feels much closer now. It really makes you wonder, doesn't it? What new kinds of personalized health insights become possible when AI can finally make sense of the beautifully fragmented, messy, but incredibly rich data of our daily lives? Definitely something to think about. Thanks for joining us on this deep dive.